due tomorrow evening. Hopefully that's not a stressful thing for you. We're looking for just like a paragraph or two saying like, hey, this is what we're going to do, this is who I'm working with. The one thing I noticed with some of the emails I got from students with ideas, which is great, feel free to reach out. It's one thing to describe a visual effect you would like to achieve, and it's another to describe how you're going to do that. What I'm looking for is the latter, right? So like saying I'm going to render a rainbow is cool, but there's a lot of techniques out there, some of which are very complicated, some of which are very simplistic, and well, I'm not terribly worried that you guys are going to choose something sufficiently difficult. I think MIT students tend to do the opposite of that. I actually want to make sure that like you have, like if I sat you in front of your computer, you would have something to do, right? You like have a concrete thing in mind beyond like this is a visual effect I want, right? So I'd like just for a rough outline of like this is how we go about implementing. Yeah, so that's your course project. Remember that essentially it's divided into 4 pieces, right? There's a proposal, there's a check-in in a couple of weeks where essentially I'm just looking for evidence that you started. And you laugh, but that is a direct result of the first time I taught this class. Then finally there's the report and the presentation, right? And it's extremely open-ended, and so I think most students do pretty well. And the best ones can get a free trip to SIGGRAPH. So that's our basic set. Any questions about the project proposal since it's due tomorrow evening? Feel free to put on Piazza if you have ideas and questions. You want to know like is this reasonable or like I'm excited about this, but I don't know what is the normal way to do it. And I can attempt to give my best guidance on that. Yeah, let's agree that like not everybody has to do a particle-based fluid simulator. Kind of tired of hearing that. Okay, so that's our basics on the project. And then on Thursday is your midterm exam. It is drafted. In theory, our TAs have taken it. Yeah. So they see Larry survives. He's here. Yeah. So tomorrow morning I have office hours. I'm expecting to see some of you guys with questions about that. I'm going to have to change my office hours, unfortunately, a little bit. And maybe I'll try to extend them while I'm at it. There's a meeting that the department asked me to go to from 10:30 to 11:30, which is like possibly irritating. So probably we'll do something like a split iteration of this way. Remind me in class, we'll figure it out. Any questions about your exam? I know a lot of boring procedural stuff today. This chair is here. Yeah.
No cheat sheet or anything, right?
Can you cheat?
Like no cheat sheet.
No cheat? Yes, cheat sheet. Yeah, so I think it's what? It's 1 8.5 by 11 sheet. Feel free to write microscopically. I don't care. I've tried to regulate that over the years and it doesn't work. So whatever you can fit on an 8.5 by 11 page, go for it.
Just one side or double side?
2 sides. Yeah, and 6 sides if we can pull it off. Yeah. I saw another hand somewhere. Yes?
Does it have to be written? Or can we just type?
No, you can type. You can use a typewriter, stencil, whatever you want. Yeah. Any other questions? Excellent. So as usual, I wrote it to be easy, and it probably is extremely difficult. The reality is, it's like if everybody does poorly, then it says you all did well. Yeah. So it doesn't actually. But really, it's just an exam, and our goal isn't to punish you guys. Most students make this and do pretty darn well. Okay. Any final thoughts, feelings? Okay. Cool. And the lecture covers everything up to and including. Well, maybe I'll find a reason why it's including today's lecture. That's the policy. Okay. Right. So today we're going to talk about shadows, and shadows are also the topic of your last homework before your project. Yeah. Has anybody given it a try, or at least run the sample code? Killed it. Well, you should, because it's cool. So essentially, in your last assignment, you're going to implement a shadow map, which is a famously headache-style graphics task, as was most of your homework, because it turns out graphics programming is kind of a headache. But it's a fun one too, because you see like really clearly why ray tracing and rasterization are like completely different ballparks in terms of how you're implementing them. Okay. Great. So today we're going to tell you a little bit about the algorithms behind shadows, and then you're basically equipped to do your last homework. You can give it a start, and I encourage you to start early. I always say that and nobody listens, but really it's a big pain in the tuchus to get shadow maps right. At least if you're like me and dyslexic, like your camera goes this way and your shadow goes like that way, and like all that kind of crazy stuff tends to happen. Okay, right. I went through a bunch of different universities' graphics classes, and I was really entertained that they all start with the same set of slides about why shadows matter. Personally, I think we can all agree that shadows are things that somebody might want to render. But in case you're not convinced, we can spend a few minutes talking about why people in computer graphics care about shadows. For one, in computer graphics, we tend to render the real world, and I think we see a lot of those. So I think that's really the beginning and end of the story. It sounds like a Facebook message. But the reality is that the shadows tell you quite a bit, right? They tell you about depth and the position of the light and so on. And of course, there's some fun images that really throw people off, right? Like here's a great, this is actually a photograph, I don't think it's synthetic at all, right? Where you can see that like there's a little oil splotch on the ground. And at least to me, like it looks like the sky is levitating. And so anyway, this is all just to say that really, you know, there's one of the things that you learn a little bit in ray tracing, but even more so in the raster pipeline is that with every visual effect you add, you pay, right? You pay in employee hours coding, you pay in CPU time, and especially in the rasterization pipeline, where you got to hit that 29.97 frames per second, or your viewer's going to be unhappy. The shadows we're going to see are a pretty expensive algorithm, but in some sense it's really like a must-have in almost any 3D environment. And so, you know, this is something that people have studied classically forever, right? So here, obviously, even if I removed the plane underneath these balls, I think you guys would perceive these two scenes quite differently. And so you can see that shadows are not just like a fun artistic effect, but really actually are built into your perceptual system as a good cue. And people have known that for a long time, right? I mean, you know, portrait painters and so on all used shadows both for you know, adding realism to scene and actually as an artistic technique, right? So one of these popular, it's not medieval, I would say colonial art forms, right? Is this kind of paper cut out of somebody's shadow. And in fact, that roughly what you're looking at right here is the algorithm that you're going to implement on your fifth homework, right? Like roughly what this person is doing is rendering a shadow map by hand. Yeah. Okay. So we've already talked about shadows once in this class. We talked about ray tracing, right? And then since your exam is coming up on Thursday. By the way, I've only heard from one student in this class with accommodations and nobody with the conflict. So I'm assuming that everybody other than that one student will be here. And if you're not, you will not get a passing grade on your exam. Sorry, should have said that before. Right. So in the ray tracing pipeline, we talked about shadows, and the way that we did it was by using secondary rays. Remember this? So I render my scene, and I figure out that the ray coming out of my eye hits this object here. And I'm experiencing it right now. And then I cast a ray toward the light bulb, and as long as the point here that isn't occluded by something in between, I render it with lighting, and otherwise I don't. And so this is one of these extremely simplistic algorithms for shadows. But think about it from the rasterization perspective. Would this be an easy algorithm to get to work in raster? Not really. Do you see that? Because like, well, what would happen? Well, probably, you know, how do I determine what's on top here? Would be using a pixel shader or a fragment shader. Yeah. And the fragment shader doesn't know what other objects there are in the scene, right? I just draw one object at a time. But in order to figure out if my shadow ray hits something, I need to iterate again over all the objects in my scene and intersect, right? And so that second inner loop is one that I simply can't do in the raster pipe. Does that make sense? We're back to the drawing board. But the shadow ray philosophy, as it were, is one that still applies to us, but we're going to flip it backward. Yeah? So in particular, what's going on here? When I render this point here, and I want to figure out if he's in a shadow or not, there's sort of two dual views of how to talk about it, right? So here, what did we do? We cast a ray out from this point and intersect all the objects in the scene. And remember the way our lectures in ray tracing were structured, right? We first talked about this ray cascading thing where you just shoot a bunch of rays out from your eyeball to figure out what's visible. But notice like that keyword I used here, which is visible. Yeah? So in a sense, what points are rendered and are not in a shadow? In other words, what points get lit by this light bulb? They're the ones that are visible from the light bulb, like the light bulb is an eyeball. Yeah? And that is going to be the key observation that we're going to use today. And this leads to a technique called shadow mapping. The idea is I'm going to render my scene twice, or n times if I have n light bulbs, n plus 1, because you also have to just render the scene. Yeah? Where I'm going to render the scene from the perspective of the light bulb, and that's going to tell me everything that gets lit. And then I'm going to make a pass over the scene, from the perspective of the viewer, and with that additional information, I'm going to be able to have shadow information. Yeah? It's going to be a completely different technique from what we talked about ratios, which is kind of cool. Yeah. Shadow maps are famously, like if you talk to like graphics professionals, they're famously tough to get right, and even harder to get to look realistic, because we're going to see that aliasing and so on are really big problems in this area. But that's life in the city. Okay, so we'll talk a lot about shadow maps, and then we'll talk about some other techniques. These are fun for your projects. So for instance, shadow volumes are a cool idea that was very popular in the mid 2000s. It's useful for certain, like if you want really detailed shadows. But then for really complex scenes, they're not terribly good. Right, so shadow maps have been used basically since the beginning of the GPU world. And in fact, if you look at the early figures which were demonstrating Pixar's RenderMan software, which was not real time, right? But it sort of had what we now would consider a GPU style architecture. Right? RenderMan has all these shaders and so on. And then in fact, you'll see all these figures which, remember the very first lecture in 8 through 7, which is cute animation with the dancing lamps. In fact, it wasn't just rendered from the perspective of the viewer. It also was rendered from the perspective, I guess in this case, the perspective of the characters, which happened to also be the lights in the scene. Yeah? And so you can see that here, right? So here's a shadow map. Let's see if I can get it. So this would be the shadow map of just a light bulb sitting above the scene somewhere. This must be the shadow map for the grown-up light bulb, and this must be the shadow map for the scene. Okay. I like you a lot, but if you could not flash your watch in my eye, I'd really appreciate it. Okay, right, so this is a really key idea in the graphics world. That essentially, these are equivalent statements, right? That a point is lit, and that it's visible from the light source. And this is a nice duality that we're going to leverage today. Yep. And we've essentially already talked about how to do visibility in raster pipeline, right? This is the depth buffer. Remember, the depth buffer is what resolves the subtop. Yeah? So to do shadow calculation, what I'm going to do is essentially render the scene from the perspective of the light bulb, and the only thing I need to render is the light bulb's depth buffer. It doesn't need to know the color of that what it's looking at. Yeah? Our color doesn't really make sense because the light is what makes the color. Okay. With me for a high level? Cool. All right. So right. With a tiny bit more detail, the shadow mapping algorithm takes place in 2 passes. This is a new vocabulary for us. So in ray tracing is sort of a one-pass, well, it doesn't have to be, but it's typically a one-pass algorithm, meaning that, remember in the ray tracer that you guys coded up, there's some for loop that's like right after the main in your C++ that just loops over all the pixels, and it did that one time. Yeah? There weren't a bunch of for loops over the pixels on your screen. Yeah? The typical way that we get cool effects in raster is by doing multi-pass rendering, meaning that I'm going to call my render function many different times, collect a bunch of images together that are all useful and give me evidence, and then combine them all together into one nice-looking thing. Right? And shadow mapping is sort of our first example of that. Right? So my first pass is going to be to render the scene from the light bulb, and then my second pass is going to render the scene from the camera using that information. Yeah? Incidentally, something that for some reason always trips up graphics students, I'm using the word render. It doesn't mean I display it on a computer screen, right? So in this case, it just gets written into a buffer on my graphics card that's going to be useful for drawing a scene with shadows. But I don't actually have to show the intermediate. Yeah? Okay. Right. And essentially all the shadow map is the Z buffer from the light's perspective. Okay, and we're going to talk about how that's useful here. And it's going to require a little bit of tricky computation to get this just right. Right. So now let's see what happens when we render the scene from the camera's point of view. Yep. So here, you know, in our first pass, what happens? I draw the scene with my light. I have point X and point Y here, and these are going to be the right depth buffer. Yeah. You know, so maybe the depth at Y is 4.8, the depth at X is 5.0, whatever. And this is the first pass of the scene. But now my eyeball rather, is sitting somewhere else. So what's going to happen? My eyeball is going to start generating fragments for the sphere, for the plane, everything. Yeah. And let's say that I generate a particular fragment at like X prime and Y prime. And notice that these are both visible from the eyeball, but X prime gets lit and Y prime does not. Yeah? So how am I going to determine that? What kind of calculation do I need to do? It's basically kind of like a texture lookup. Do you see that? So, you know, my point X prime, I know where the light is, by the way. That's a uniform piece of information I can give to this shader. Yeah? So what do? I render point X prime, and he has a particular depth from the camera. Is that the same as the depth of the light source? No, right? But I have some XYZ position of where that point is in the world. And now I can compute the position that this thing would appear on the image from the light plane. Do you see that? This is going to be an annoying change of coordinates. Yeah, let's maybe draw what this looks like. Right? So I have, here's my light, here's my eyeball. I think this is the sort of typical scene people draw for this stuff. Here's a plane. My ball is kind of big, so it obscures most of the light. Right, so there's some shadow like that, right? Okay, so what am I going to do? Well, I'm going to cast, I shouldn't say cast array anymore, but I'm going to render the floor and generate a fragment here. And this fragment, it has a position on the screen and a position in 3D, both of which I have access to. Yeah? But I can also have access to the projection matrix that the light used to make his the depth image, right? So now, inside of my camera's shader, I'm going to apply the projection matrix from the light. And what that's going to give me, remember that the light already has this little image kind of rendered in front of his perspective here. It's going to give me a particular pixel position on the light image, which is where it would appear if this were in the light's depth map. Okay, so now, what do I have to do? I compute the full distance from this point to the light bulb, and then I look inside of the light texture map, and I say, are those two numbers the same? Right? And if they are, then this point gets lit, and if they're not, then it doesn't. Did I totally manage to butcher that? Do you guys get the high-level point here? There's a lot of camera transformations happening in this algorithm. I rasterize the scene from the perspective of my eye. I generate a fragment. I figure out where that fragment would be from the perspective of the light camera. And then if that fragment was generated in the light's perspective, then I draw it as lit over here, and otherwise I don't. Yeah? And that's really just a texture lookup in this image here. Isn't that sneaky? I think it's really sneaky. This is a cool algorithm. Yeah? You guys actually just eyeballing this terrible drawing I've drawn for you on the board here. Can you guys tell me some problems? What's going to go wrong with shadow mapping? Yeah?
This is just a quick question, but like, how do you take care of like the shadow gradient? Like how far
that's a great
away
first question. Yes. One thing goes wrong is this is a hard shadow. Right? You're either in or you're not. Yeah. We're going to come back to that in a minute. Using something called percentage closer codes. Yeah. What else? What other artifacts do you expect to see? Yeah, so there's an artifact called self-shadowing, right, where I say, like, is this distance the same as the distance that this eyeball thinks is that distance? Well, they could be close, but maybe just due to rounding, they're not quite the same, right? So there's some tolerance that has to happen there. Yeah?
You're sampling the shadow buffer like slightly differently than the
Yeah, this is a key thing. I put a grid here, right? So there's a resolution, there are now two resolutions at play. There's a resolution of the rendered scene, and there's a resolution of the shadow map, which is typically low, right? Because this is just kind of some convenience thing, right? So in reality, my shadow probably looks like a little blocky thing, you know? By the way, for that particular artifact, where's that, like, really a problem? For dramatically lit scenes, right? Like, so if I have a light bulb over here, so the shadow is that, right? Then like 1 pixel in my shadow map over here covers a ton of ground, while 1 pixel up here covers relatively little. So in fact, it's not even uniform. By the way, many of you guys have probably seen this. If you play in old video games and you see a shadow, often a shadow will have that kind of blocky boundary. And there's one last interesting issue. Remember that in rasterization, typically we don't draw everything in front of the camera. We only draw the stuff inside of the view frustum. So in that case, what could go wrong? Well, the shadow rays just kind of stop, right? Like if I put the view frustum, remember, as some polygon sitting here, right? Then it could be that like this point actually does get lit, but it's outside of the frustum of the light bulb, and so it just doesn't even realize that. These are all tricky artifacts. But the basic algorithm is kind of cool, and it's a really clever trick, right? That essentially, by rendering the scene from the light bulb's perspective, that gives you all the information you need, at least to first order, to draw a shadow. Yep. And so that's the basic trick, right? Is you compute this point, you figure out where that is on the image plane of the light bulb, and then if this depth that the light bulb has in its image agrees with the depth that you compute, then you keep it. Any questions about the basics? Then we'll go into some implementation. It's a cool algorithm. Can't say that enough. I really like this stuff. It's conceptually cool, and you can imagine it's just like a giant headache to get right. There's a lot of opportunity for error here. Yeah. Okay. Right. So one of the key tricky things here is that you have to be able to project things into the image plane of this light source camera. And one question you might come back to is there's a lot of different types of light out there. And you can ask, well, how do you capture all of these things? And of course, it's nothing more. This is a great lecture to have right before your midterm, because these are just different camera transformations. You guys see that? So for example, here, right, this looks like a view frustum, and that's exactly what it is. It's like a perspective camera, which makes sense. Like here's your eyeball, there's the spotlight, and they have sort of the same shape. But already spotlight is like something that we considered an extra feature in our ray tracer, but somehow that's actually the easiest light to have in the shadow mapping algorithm. Right, so that would be perspective projection. Let's say I had a directional light, like a big, you know, like when you have a photo shoot, as I often do. They'll have like these big sheets that they hold up with the, kind of light reflector surface to get that nice soft, I don't know, kind of a greasy guy. So in this case, what kind of camera transformation would you probably have for your light? Your view frustum is a cube. Yeah. Yeah, an orthographic projection. You know. And now let's say that I have a point light, which was, remember the basic one we had a ray tracer, right? So this would be just like a light kind of sitting in space, radiating everywhere. What would I do? How should I go? This is actually a trick question. This is dealing with the point light is kind of annoying in this algorithm, because when you say render it from the perspective of the light bulb, well, the light bulb doesn't really have a perspective anymore. Yeah. So there's sort of two things you can do. You can do some crazy spherical projection, like put a big lens around your light. That seems kind of complicated. So in practice, what we do is we put a cube around the light bulb, and we say, oh, no, it's not a point light. It's actually 6 spotlights that just happen to line up. Yeah, and that's the sort of typical way to get a point light source. Do you guys see the connection between camera projection and shadow map? Yeah. This is so cool. I love this. This is so neat. Okay. Right. So yeah. So this is this multipass technique, and essentially, by the way, do you think that the shadow map pass, even if the shadow map has the same number of pixels as the final image you render, which one do you think is faster? Definitely the shadow pass, right? Because all it needs is depth. It doesn't need to do your EF. It doesn't need to do anything crazy. Yep. And it's less memory, right? Because you just need one channel, which is dead. Cool. Okay. Right. So this is like kind of a typical image here. Let's see if we can figure out what's going on in the scene. It looks like my camera is looking down on the top of a cube, right? There's an edge of the cube and a sphere. These tend to be like, at least to me, really, I don't know, somehow counterintuitive images to look at, but you'll get used to it because they're on your home. Right. One small detail. Remember we talked about normalized device coordinates, which are essentially the idea that when I render my depth map, I typically scale the view frustum so that the close plane is at like, I don't know, -1, and the far plane is +1, or like there's some prescribed range. By the way, the old slides might have said 0, 1 or something, but I'm not going to worry about constants in this class because they're engineering decision. But the basic idea is that I rescale some range of depth values to like +2 -1. And this is, of course, something you do a little careful to invert in your shadow mapping code. Right, so here's the basic outline of what your shadow mapping code will look like on your homework, right? So you're going to set a frame buffer, and what this is doing is just kind of like handing you a piece of paper and saying, like, this is what you're going to draw on for now. Right? So in this case, it's going to set it to the shadow depth buffer, just a little piece of memory which is dedicated to keeping the shadow for a particular light bulb. Notice, by the way, that the memory usage of this algorithm increases with every light bulb that you add to your scene, which is a little bit problematic. Right. Then you're going to draw the scene from the perspective of the light. Then you're going to change the camera to be the perspective of the camera, and then set the frame buffer to probably still not a frame buffer you're going to render, but then you'll draw it and then you'll flip. By the way, I noticed this is something that I should have covered in the rendering class, or the rasterization class. There's a technique called double buffering, which I think is totally natural, but we often forget to cover it because it's so natural. Typically, so your GPU has a frame buffer that's basically wired right into your computer screen, right? Like you write some colors on there and they're displayed. Yeah. Do you want to write into that? Like when you're rasterizing a set of triangles? Probably not, right? Because then what you're going to see is one triangle drawing itself in a type. Yeah? So a more typical thing to do is to have two buffers, one of which you're drawing in and the other you're displaying, and then a binary variable saying which of those two is getting displayed. So what I do is I render over here, I display over there, and then when I'm done rendering, I flip that binary number, and all of a sudden my display goes over there, and then I render over here. The reason being that I don't want to have to copy all that memory over, so you just flip back and forth. Yeah, this is a technique called double buffering. Yeah. Okay, so, right. So now we should fill a little detail about that shadow mapping pass. Yep. Right, so, right, so this is the pass where I'm actually rendering the scene to figure out whether I should light it or not. Yeah. So I'm at a particular fragment. So this X world here maybe is the position of the fragment in 3D, which I've generated, but I'm rasterizing the triangle. Yeah. And now I hit it with the camera projection for the light bulb. Yeah. Right. And what I get back is some depth value from this thing. And of course, there are two things that go wrong, right? The first one is that remember that it could be that like your texture image is in the 0, 1 range, your normalized device coordinates are -1. Essentially, one thing you have to be careful about is that a lot of rescaling happens inside of your code. And so things that probably should somehow philosophically be linear aren't, because you normalize by some magic number. But even there, so let's say I figure out the right thing, and I have the depth that I read off of the shadow map, I have the depth that I actually computed, and I want to compare them. Right? And I'm in a shadow if the occluder depth is less than the depth of the fragment. Does that make sense? What could go wrong here? You guys actually already mentioned it. Rounding, yeah? Right? Because essentially, what happens when I'm actually rendering the lit scene is these two numbers should be exactly the same, right? But numbers are never exactly the same on the computer. Yeah? That's sort of a takeaway you should get from this class. Yeah? And so reality is that you need to add, just like you had all these epsilons floating around inside of your ray tracing code, the same self-shadowing artifact appears here. Yeah? So here's an example of what this looks like. So here we rendered a cube, And on the face of the cube, apparently numerical precision was such that every once in a while the cube ended up on top. Every once in a while the shadow of the cube ended up on top. And that's a pretty common thing. Yeah? On the flip side, if you change your epsilon to be too big in your shadow map, then your shadow has a bite taken out of it. Right? Which makes sense because now this depth and the depth of the face are somehow similar. This is exaggerated. I don't think you would see it in fact it's in practice. But it's just to be weird. Does that make sense? Cool. Again, conceptually easy, really annoying to implement. Can't stress that enough. I'm trying to warn you now about your homework, in case you haven't gotten the message. Yeah? Okay. Another big issue, of course, is aliasing. This is an issue in computer graphics, but it's particularly bad in shadow map for kind of similar reasons to why we needed bitmaps for textures. Remember in bitmaps for textures, I looked at it like an object kind of in a skew way, and maybe the far part is alias and the near part is not. Right? Somehow something is similar is happening here, right? I have this very dramatically lit pot here, and the farther shadow rays, right, essentially take what was maybe a small pixel in my stencil or my shadow buffer, and make it take a pretty big piece of the plane in the image that I actually rendered. Right, and that's particularly a problem for these kind of long shadows. How are we going to fix that? This was came back to your question. Well, we'd like to do some anti-aliasing, but what wouldn't make sense? So let's say that I have a depth map, yeah, and I'm rendering the teapot, right? And I notice, like, you know, the teapot is some depth, the plane underneath the teapot is some other depth, right? And I generate my shadow buffer, right? And I have two adjacent pixels, one of which is on the teapot, one of which is on the plane, right? That's exactly this interface here. Would it make sense to anti-alias that image? It actually really wouldn't, right? Because what I would get is like depth values somewhere halfway between the teapot and the plane, and like that's not particularly meaningful. So that leads to a different technique here. This is called percentage closer filtering. The basic idea here is that if I have this depth map, like maybe this is the teapot, this is the plane, then like putting a depth here of 25 would be a bad idea because who knows what that really means? You could, you get some kind of image, but right. So instead, typically what people do, which is kind of sneaky, is they use when they do the texture lookup in the shadow map. Remember, this is a texture lookup. Like I'm just reading off the depth of the shadow map. I use a boring texture map. Like I look up, I don't interpolate. There's no bilinear stuff going on. I just round to the closest pixel. But I do anti-aliasing in the internals of a pixel. Okay, so in other words, I'd say like, well, if I perturbed my position a little bit here, would I still be in the shadow map? And I kind of average. And so this technique is called percentage closer filtering. The idea of like what percentage of this pixel is inside of the shadow and what isn't. And what it does is it makes soft shadows, like what you're seeing here. And you can see that essentially what you're seeing here is the grid on which you did that percentage closer filtering. Yeah. Notice I said soft shadows, but these aren't actually soft shadows. They're artifact shadows. You see that? Because like, why are they soft? They're soft because I couldn't resolve this edge. It has nothing to do with the light bulb. Yeah. But in a sense, somehow what's going on is like everybody wins. You know, you might want a soft shadow effect, and you got it, but you didn't get it for physics reasons. You got it because of anti-aliasing. Of course, this is making a feature into a bug. The reality is having a hard shadow underneath an object is kind of hard to do in this algorithm without getting this blocky edge. Yeah. Okay. Any questions so far? Cool. I like this stuff. Right. So the other issue, or another way of taking care of this issue, is to notice that you kind of need a different resolution for your shadow map in different places. Do you see that? Like when the shadow map is particularly skewed, then somehow the pixels in the shadow map are taking a large part of the geometry, whereas when they're very close, you don't need that. Yeah. So in other words, like just a generic shadow map plus a very big range of depth is really problematic. Right? So maybe I have a light bulb somewhere like over here, and what you're seeing here is the image of every pixel of the shadow map kind of just cast onto the scene. And you can see that some are far larger than others, both in terms of your camera and just in terms of the plane that the light is hitting. Yeah. Right, so a different way of putting it is that there's too many texels. By the way, we call them texels here instead of pixels because they're the texture are in the distance and there's like sort of not enough in the point of view. What do you think people do? They make more than one, yeah? So maybe you take the view frustum of your what's it called? Your light bulb, and you divide it into not just one frustum, but multiple frusta. Yeah. Right. So in other words, maybe you make a picture that looks like this. So here's my light bulb, right, and then here's maybe my shadow map. He has some frustum which I can never draw, which looks something like that. This is an orthogonal light in this case. Yeah. And essentially, one thing I could do is just do a second shadow map with a different frustum, right? Oh man, what are you drawing? Big, right? And these three shadow maps will cover different objects in the scene, right? Because these guys would get, if I have an object here, it would get clipped in this frustum and vice versa. Yeah. But one reason to do that is that the objects that are close to the light bulb, you kind of need more pixels of resolution in your texture map to resolve that shadow. Right? Because if you're really close to the light bulb, you're like some little itty bitty sphere right here, you still can cast like a giant shadow. So it makes sense to have a lot of resolution there. Right? And so if you think about, I can draw the 2D version of this because I can't draw. Then separating into multiple frusta kind of makes some sense. Right? So in effect, I have more resolution for stuff closer to the camera. This is called a cascaded shadow map. So typically what they'll do is they'll kind of take the frustum and put 5 different shadow maps at different depths. Does that make sense? Cool. So here's an example of what that looks like in this kind of complex scene. And you can see that, like, some of the things that are, I think, kind of have these sweeping shadows on them. The edge of the shadow is actually still pretty sharp, and the reason is you have more resolution, the closer frustum. Okay. Of course, many of the drawbacks of this technique are pretty similar to the drawbacks of bitmapping, right? Because now you have multiple levels of resolution that you're kind of coping with at the same time. And so what will happen is, of course, you have this edge between one frustum and another. So I think typically what you would do is maybe actually have these intervals overlap a little bit and blur it out a bit. Yeah. But the good is we get really state-of-the-art quality. Like I think, like at least around like a couple of years ago now, this is really what people do in the game engine pipeline, right? Because essentially what it does is like the computational complexity of this shadow map and this one are the same. Do you see that? And they cover different amounts of volume, which is on purpose, right? You're putting more of your work on objects that are closer to the light. Okay. Any questions about this trick? By the way, if you're looking for like good course project ideas, these are also kind of good. Yeah. Okay, so that's shadow maps. That's all you need for your homework. But there are many shadow algorithms out there for rasterization, and it's worth kind of briefly noting a few. In particular, there's a technique called shadow volumes, which I think really had their heyday maybe 10, 20 years ago, are a little less popular now. But they did lead to development in GPU architecture, which is worth being aware of. And is a way to get nice sharp edges for your shadows. And this is a technique called shadow volumes as opposed to shadow maps. You probably, from that phrase, guess more or less where I'm going with this. So the basic idea here is that if I have some polygon that I'm rendering, then there's a polytope worth of stuff that it occludes. Right? In other words, like if I have this square here, and there's this kind of funny frustum shape from the light bulb, which are all the things, if you sit inside of this guy, you are not lit by this light bulb. Did I get that right? Yeah, I totally did. Yeah. And so essentially the idea of a shadow volume, you say, well, this whole thing is a shadow volume. I'm going to mesh not just this top part, but maybe I'll make a mesh of all sides of this frustum here. Yeah. And now if I render this frustum object, then I'll also see the side here. Yeah, and that's going to tell me something about whether or not I'm inside of that object. It's a sneaky trick. Yeah. Right. So like the naive version of this guy is to look at this green triangle and say, well, how can I, one way I can figure out if it's in a shadow, yeah, is let's say I were ray tracing for a second, and I ray trace this. I could count the number of times that my ray intersects a shadow volume. And can you guys tell me when, if I count that number of times, when am I shadowed and when am I not? Exactly. If the number of times that a ray from my eyeball to this object hits the shadow volume is odd, then I should render this thing in a shadow, and if it's even, I should, right? So think about the case where the triangle is behind the shadow volume, right? So now when I send a ray through the shadow volume, it enters and then it exits, and then it sees that back out, okay? So those two kind of cancel out. You can imagine, like, in case you thought shadow maps were annoying to implement, this is even worse, right? Which I think is why this is largely kind of unpopular. Right, so here's the basic idea is that I count the number of times I intersect the shadow volume, and then I use the parity of that to determine how I render it. Notice in the rasterization pipeline, this is going to get annoying. I'm now going to need 3 passes over my image. Right? The first one is to render basically just the Z buffer for the geometry in my scene, ignoring the lighting. And why am I going to need that? Well, now I'm going to render all of these different shadow volumes, and I'm going to increment a counter as I do that every time I see a pixel that's intersected by shadow volume, or by a surface on the shadow volume. But if it's behind the scene geometry, I should increment my counter, right? So that's why I need the Z buffer from the first pass. And so that's pass number 2, and then pass number 3 is to do the lighting. And in this case, you look at that odd even number, and you decide what you're going to do. Yep. And this algorithm is not terribly important in the sense that I don't think many people implement it because it's really hard to get right. But it did lead to a sort of a generic idea, which is called the stencil buffer. The idea of a stencil buffer is that it's yet another buffer in your graphics card. By the way, you shouldn't think of all these things as like little physically marked off spots in your graphics card. These are just names that we give to arrays. But this is an important one. And the stencil buffer is like a buffer with integer values in it instead of double position or floating point, right? Because all I need to keep track of is whether I'm in the shadow volume or not, right? I don't actually have to keep track of where the shadow is. And so when I do that shadow pass, all I do is as I rasterize every face of these shadow volumes, I just take every number in the stencil buffer and I keep flipping its bit back and forth between 0 and 1. Yeah? And then what do I get at the end of the day? Well, I get a mask, like a bunch of 1s, at exactly the places that should or shouldn't get lit, depending how it yeah? And this is called the stencil test. Right? So essentially, it gives you some binary variable for how to render. Does this idea make some sense? Right. Cool. So why would you want to do this? Right? It seems like a giant headache, right? Like I have to form these weird shapes, and then I have to rasterize not just the object, but now the sides of these shapes, and then like twiddle a bit back and forth for every time that I see it, and it's not included. Which means I need a 3-pass render, right? Z buffer, shadow volume, shading. Well, think about it from like kind of a Fourier or anti-aliasing perspective, right? All 3 of those passes took place in the image plane, right? They didn't take place in some weird image I'm rendering from the light bulb's perspective, right? And so a lot of these aliasing issues are sort of taken care of, right? Because your detail is already just on the order of what you have on your screen. That makes sense? So that's sort of the advantage here, is you get very detailed shadows because in every pass, like when you render this shadow volume, you really see this edge at exactly the resolution of your screen. Yeah? And so you get nice sharp shadows this way. Right, so this is our sort of summary of this algorithm, right? You initialize your stencil buffer to 0 everywhere, you draw your scene, get the Z buffer, and then you do this thing. And do you guys know why they call it the stencil buffer? It's totally reasonable, right? You have a bunch of binary variable, like 1 for every pixel on your screen. And it's exactly like this, a stencil is like a piece of paper you spray paint on, and then you only see the part that is a hole. Yeah? So here you have a bunch of binary variables saying whether or not the fragment is in a shadow, so it's called like a stencil. And you're like painting inside of it, the lit stuff. Okay. So this trick. Computing shadow volumes is just like a giant headache. Right? Like you probably wouldn't want to do it for every single triangle in your scene, right? So you might do something crazy, like I know all the geometry in my, like maybe I'm making my video game and there's a bunch of static objects that I know I'm gonna have to render. So I'm just gonna go ahead and do a bunch of math offline to compute a really nice, simple shadow volume ahead of time. So for instance here, I'm rasterizing this house. Notice, do I need a shadow volume for the tree? No, right? Because the tree is just completely occluded by the house here, right? So essentially, one way to view that is that the shadow volume for the tree is contained within the shadow volume of the house. Yeah. So that's not the kind of analysis that you can really do online, but you could, like, if you just run in the neighborhood, you could do it often and keep track of this crazy shape that's like a triangle mesh. Yeah. So that's the thing people do. But of course, you're going to run into trouble if you have a dynamic scene where you can't do that often. Right. And so they're a little passe. I think it's really hard to do it efficiently. Some people have managed. They're particularly tricky if your light bulb moves, because then your shadow buffer, your shadow volumes are shrinked. You gotta like start over again. Yeah. And in particular for scenes like this one, you're just totally hooked. Right? You got an extremely complicated shadow volume you have to render, and there's a lot of overdraw. You guys remember what overdraw means, by the way? It's a good vocabulary moment. This would be like generating a lot of fragments in a single pixel, right? And in this case, that's certainly true, right? Because it could be that the shot, like maybe the light is somewhere up here. It could be there's like some itty bitty little hole that extends through the shadow volume, like the space between two leaves that you see on the ground. That's one little point of light. So like topologically, like there's a little tube cutting through the shadow volume that you've got to keep around and render, right? But for the most part, it's useless, right? It's only affecting a few pixels. But you need it there because if you happen to view the scene from just the right angle, you'll see it. Yeah. Right, and especially on like tile-based, like cell-phone GPUs and so on, this is just not a technique that works very well. Yeah. Good question. If your camera position changes, do you need to recalculate the shadow number? How many of us vote yes? How many of us vote no? How many of us are wearing headphones? Right, so, yeah, no, if your camera position changes, the shadow volume actually doesn't, yeah? Because the shadow volume is just the volume of stuff that gets covered up as the light gets, right? As the camera gets. Yeah, it's a great question. Any other questions? Okay. Great. Okay. Right. So there's all kinds of. If you haven't caught on by now, shadows are a big topic in graphics, and getting them right is challenging, and it's one of these engineering decisions that you have to make pretty early on when you're designing 3D software, which is a little surprising. And so there's a lot of people that put a lot of thinking into this. In fact, there's an entire textbook called Real-Time Shadows that you can get. Of course, they show off all the cool stuff in this, on the cover of the textbook, right? You can see how crazy the scene is, right? There's like fog in the air and this very complicated light-emitting object, and it's going through a tree, right? They really, I'd be surprised if, oftentimes what you'll see, by the way, in these demos of these shadows, buyer beware. A lot of times when you go to GPU companies, I won't name any names, they'll advertise that they can do certain shadow algorithms at real-time rates, and often that's true if literally the only thing happening in your graphic system is drawing shadows. That doesn't mean that it's necessarily a particularly practical thing to do unless you have 2 GPUs or on one of whose job is like just to draw shadow maps or something, right? So anyway, usually you want to take like the time they say it takes to do this stuff and multiply by like 5 or 10 for like humans that write normal code and don't work at a hardware company, can't do weird stuff. Yeah. Okay. Just for fun, we'll spend just a few minutes talking about one other trick, and we'll end a little early because I know your exam coming up. And that's an idea of deep shadow maps. This has nothing to do with deep learning for now. I don't know. Maybe somebody could find some reason why they're related to These aren't really used in real-time graphics, but for rather for rendering things like foggy light or like the murky water kind of stuff. Notice that there are shadows in murky water, but they're weird shadows, right? There's sort of like a decay that happens. Yeah. And these are often used in movie production, actually. This is actually slowly changing. So it used to be the case that movie production was really a combination of raster and ray tracing. I think more so the raster part of movie production is becoming less relevant as computation becomes faster, but it still exists. But how would I use shadow mask to draw a scene like this? So I've got a bunch of pipes that are emitting smoke, and I've got a light that's shining right through. So notice there is a shadow, right? Like the smoke is casting a shadow on the ground. Yeah, it's kind of fuzzy. And it is just a little bit, let's be engineers for a second. But how can we solve this? Yeah.
I guess you could like add a little bit of randomness in that general region to like say that, you know, whether or not you've intersected like a point in that fog cloud.
Yeah, that's true. You could like kind of say, I know that I'm underneath the point in the fog here, and I'm going to flip a coin as to whether or not I actually light it that way, right? My bet is that would lead to kind of a noisy shadow. It's an interesting idea. Yeah. And actually, by the way, pretty physical, right? I mean, fog is roughly brownie motion. It really is nice. Yeah.
Maybe so. Like normally, when you calculate depth map, so the camera just like have a hard cutoff for like the depth.
Yeah.
Maybe like for opposite fog, it isn't a hard cutoff, so you can push further back. The sense of like almost diffusing the light, but really hard cutoff is just fog.
That's a great idea. So that's actually roughly. Very roughly. I'm going to choose to interpret it as roughly what people actually do to render these kinds of scenes. Right. So, and this is this idea of a deep shadow map. And to paraphrase a little bit in a way that suggests the right answer. Roughly, you can think of a shadow as like some kind of binary function. Like what it's saying is, below some depth I light it, above some depth I don't. Yeah. But you could also imagine taking that binary function and making it fuzzy, right? In other words, I could say, like, I could draw a ray from my eye outward and make a plot where the x-axis is distance and the y-axis is how much light got through, right? So for the shadows we talked about so far, that function would look like 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, right? But in this kind of scenario, what happens? Well, the farther I get away from the light bulb, a little bit more light decays. So a deep shadow map is to deal with things like participating media. Right? So it's the idea of participating media is it's media that participates, right? It's a it's like something that's sitting in the air but messing with how the light is moving. And the trick is that we're going to make a volumetric shadow buffer. So far we've talked about a shadow buffer as like an image with a depth. Yeah. But now what I'm going to do is for every pixel in the shadow buffer, I'm going to keep an array, so like a function of depth, which is how much light gets to that point. Yeah? So it might look something like this. Like so here, maybe I have a bunch of like kind of semi-transparent windows, right? And so underneath 1 pixel of my shadow buffer, it starts at 1, saying 100% of the light gets through. And you pass through the first window, and it goes like 75, and so on. Or maybe if you have these puffs of smoke, then it decays a little more smoothly. And this is called a visibility function. You guys get the basic idea of what we're going to compute? So essentially, instead of just like a width by height shadow map, now we're going to have a width by height by depth shadow map. You can see why this doesn't happen in video games, right? Because that would be extremely expensive. Maybe you could have a few samples and pull something up. By the way, this is actually also hard to do in a ray tracer. It's not like participating media is particularly easy to ray trace. So this is a reasonable algorithm to use there too. Right. So this is sort of a pre-processing step that happens. So one way that you might incorporate this into a video game would be you do your really expensive smoke simulation offline. You go ahead and compute that shadow map and you just store it somewhere. And that way you're not actually computing it in real time, you're just loading it up and keeping it there. Yeah. that would probably work for like maybe MRI style applications, like I want to look inside of a volume scan of your brain, where like the geometry and thing with render is kind of static. Probably video games you want your smoke to move and then your host. Yeah. Right. So then in RenderChime, you know, when I do my shadow query, now a really crazy calculation happens. I'm going to try and draw this, and you guys can tell me how badly I fit. Okay. So here's my eye. Here's a puff of smoke. And here is an object I want to render. Everybody with me so far? Okay. So now, what am I going to do to figure out lighting? And my light is maybe up there. Well, now the light has some map like that. Right? So I first do a depth path, and I just ignore the puff of smoke. Yeah. So now I get this point. And I want to know how much light gets reflected off of this surface. What's the next thing I have to do? Well, now I find the corresponding pixel in the deep shadow map. And this thing gives me some function, right? Which is saying, so this is depth, and the y-axis is the percentage of the stuff that goes through, right? So it's something like that. Yeah? Okay. And now I say, well, I compute this depth value. So far it's looking pretty similar to the shadow map. That's some point here. Yeah. And this gives me some amount. Okay, so that's the amount that gets reflected off of the surface here. Is that enough? Now I just read off that color, and that's what I rendered? No, I forgot a term, which is there's also participating media on this ray. Right? So that's the amount that gets reflected off of the surface, right? It's just the percentage of this light coming here. And now I've got to attenuate this way as well. So maybe I need a second deep shadow map for my eyeball to get this computation. So this is just a giant head. But it's kind of cool you can do this, right? And essentially it's a nice trick. Of course, typically there are all kinds of techniques people use to make this faster, right? So maybe you take your shadow map, you don't actually structure it as an n by n grid of numbers. Maybe you like try to approximate it with some simple function. I think is typically what people do. But the results are like quite convincing, right? So here's a puffy cloud of smoke. Can you guys think of other participating media for which this kind of algorithm is really needed? So another one is curly hair, right? Because curly hair is this big volume with a bunch of translucent objects that block some light, but not 100%. So here, this is with and without self-shadowing. So you can see without self-shadowing, which, and when they say self-shadowing, they just mean the hair is casting a shadow on itself. The hair is roughly a puff of smoke here. Do you see that? Like to first order, this is just some dense blob of vaguely light-blocking material. And without self-shadowing, you get hair that's like unnaturally bright. So here's another kind of creepy example where you have a hairball, which is a great. You see a lot of these hairballs in these renderings. Incidentally, another nice thing that this allows you to do is motion blur. Right? Because in some sense, your motion blur, you can think of like this moving ball is some participating medium, right? Like at any point in time, only 50% of the ball is at that point. You know, like half the time it's there and half it wasn't. Right? And so this is another technique. Because if you don't, then you're going to get something bizarre, right? Which is like one shadow for rapidly moving speed. All right. Any questions about deep shadow maps in general? This is what you're going to implement in your home. Not this. The first path. You can do this for extra credit. I'd love to see somebody try. I put that in the back. It would be really cool to see a successful project. All right, so that concludes our discussion for the day. I thought I'd save 10 minutes in case there's any topic that you guys want to cover before your midterm, very briefly. Or we can just pause. I'll hang out until 4 p.m. anyway, and I'm happy to chat with you. Okay, so we'll call it for the day. I'll stay here in case you have any questions for your midterm. Please don't let me forget I've got to adjust my office hours ever so slightly for tomorrow. And good luck on Thursday. Please turn off the thing.
I got invited by Rachel.